Right, good evening, everyone. Thanks very much for joining us today. This is something new this year. I'm going to talk about how to do a PhD. I'm not going to talk about the mechanics of it, the steps along the way. I'm not going to talk about research methods. We'll cover that very briefly, really mainly between you and your advisor. What I'm going to talk about is how to approach a PhD, keys to success in a PhD, how to go with your advisor, things like that. Things that I've observed in my the years of being a PhD advisor. I've had over 70 students. I've graduated over 70 students. So I've got a lot of experience with it. I'm going to share some with you and hope it'll be useful to you. So, and then towards the end, I'm going to talk about the one thing that makes a difference. And it'll be a letdown when I get to it. But I believe in it. I really do. So what we'll be talking about is what are you trying to achieve with a PhD? What are the objectives? And then get into the stages of doing research in general and the PhD specifically. And then spend a few pages focusing on identifying research problems and solutions. I see a lot of students get stuck there. The advisor says, will you come up with a research problem you want to solve? And the student goes, and struggles to do that. So I'm trying to give you some ways in which to approach that. Then I will get into some of the aspects of actually achieving the PhD, how to establish the research state of the art, how to read papers, which is not as easy as just picking up the paper and reading it. There's steps to make it more efficient. I'll talk briefly about writing proposals, which ties in with the preliminary exam. I don't tie this in with the qual and the prelim as we go along. Then I've got one page on the use of AI and a couple of pages on your advisor relationship. We've got about 30 slides, so we've got plenty of time. So feel free to ask questions as you go along. But I must admit, I'm not monitoring the chat. So Jinyi is, I believe. Let me know if any questions come up. So what's your goal as a PhD student? Is to work out how to run Zoom. Get rid of all that, right? It's to advance the knowledge of mankind. Right? It's simple. Right? You discover new knowledge, new ways of doing things, new ways of solving problems. The emphasis there is on the novelty. Rehashing what someone else has done is not a PhD. Go work out something new, something novel, something that's new knowledge. And this is easy to say, and it's quite doable with persistence, but it's not easy to start out with. But we're engineers, so we really have two types of knowledge that we are trying to discover. One is theory, one is application. Right? Advance the knowledge and understanding of electrical computer engineering principles and technology. These are new methods, new techniques, new theories, new algorithms, new ways of new theory. The emphasis here is on theory. For example, Shannon's communication theory would be an example of in this category. Is a theoretical concept that really changed communication. The other one, and frankly where most engineering students end up, is develop innovative solutions to complex problems. That is, work out new ways of building hardware, new ways of building algorithms to solve specific problems. So focusing on the practical problems, not so much on the theoretical underpinnings. An example here would be working out a way to improve the efficiency of the communications chip, as opposed to extending the theory, working out how to build the chips would be advanced in the practical side of engineering. Again, most PhD students in engineering end up in the second camp. So that's what you're trying to achieve with a PhD. Easier to say, harder to do. Now, I'll put down here steps in the research process. This applies to any research process, but the PhD is probably the first time you're going through this completely. And this is not a linear progression. This is really more a spiral where you're constantly working on several of these at the same time as you're progressing through solving the problems that you're dealing with. I've simplified the steps here. Identify the research problem, identify the solution. Sometimes they go in the reverse order. Sometimes you have a solution looking for a problem. And that actually is quite common, and I'll give a couple of examples of those. Analyze the state of the art, do the literature review. Now, some people actually believe you shouldn't do this. They believe that you should just be innovative without trying to be constrained by the past. That can work, and it does work in certain in certain examples. But in general, quite often, if you thought of a good idea, it's unfortunate. Someone's probably thought of it before you. And there's not much point pursuing that idea until you establish that no one else has thought of that. That is one aspect of understanding the state of the art. The other aspect of understanding the state of the art is we're generally working in mature technologies to one degree or another. And we've got to stand on the top of shoulders of others. So understanding what people have done before you and working out what's the landscape of the research area you're in is actually quite important. I'm going to concentrate largely on the first three steps, but the other steps are important. Formulate the research objectives and questions. I'll actually touch on this, but that's after you've worked out the big picture of what you're trying to do and what problem you're trying to solve and how you're trying to solve it. You can cut it down into a series of steps and a series of questions that have to be asked or have to be answered, or a set of objectives that have to be achieved. And this is a key step and a valuable step because it takes the big picture of what you're trying to do and determines step by step what you need to do in order to achieve that big picture outcome. So this is actually quite valuable, but it's specific to the problem you're dealing with. So I won't be covering that in a lot of detail. The next three bullets are where you actually spend most of your time and where I'm going to spend no time in this lecture. This varies so much from topic to topic that I can't really cover. Some of you will be using machine learning to solve a problem. Some of you will be using data analysis. Some of you will be building circuits. These will fit into the research methodology, the experiments, and the data you're collecting and analyzing. But they vary so much. That would be covering those three steps would be something to turn this from one lecture into a course. I'm not planning to do that at this point, but it's something we could consider. And finally, communicating the results. This is a very important step. There's not much point doing the work if it's not published or spoken about in the appropriate venue. And frankly, this is important to you individually. Because one thing you're going to get out of doing the PhD, and particularly continuing the research, at some point of individual notoriety, hopefully good notoriety, but you'll get to be known, and others will know you, and know of you, and know of your work, particularly as you start your career post-PhD. And you have to communicate to make that happen, to your respective colleagues who you're choosing to do. And this applies to many industry people as well as academics. Here, I'm not training you to be an academic, I'm training you to be a researcher. There's many successful researchers, even very well-known researchers. Don't think that I'm going to go to industry that matters less than me. That's not true at all. We're training you to solve problems. You'll be expected to solve problems in an industry as much as in academia. Any questions so far? They can't hear me?
The audio is not clear.
Yeah, that's an unfortunate aspect of using Zoom. I'll try to stand closer to the computer. Is that better? Does anyone say it's better? Okay, I won't move out as much. Okay. So identifying the research problem. I get many people in my office who comment on this or complain. I've been asked by my advisor to identify a research problem, and it's surprisingly common. And it's a difficult thing to do, particularly the first time round. It took me a while as a PhD student, and if you're asked to do this by your advisor, it might take you a while as well. And your advisor might have that patience for that. So I'm going to spend a few pages a few slides on how to approach this. This first slide is just a possible set of sources of your research problem. Now, hopefully, particularly if you're an RA and not working for a new faculty member, you're funded by a contract or a grant or a gift. And generally, someone, your advisor, wrote a proposal to get that. And he or she should share that proposal with you. I do this all the time with my students, but it's surprising how few advisors do this. So if you're, who's an RA in this room? Who's seen the proposal that they're working on? Good. So a lot of you have. But surprisingly, it often doesn't happen. Now, it might be the advisor's not proud of the proposal, or it might be very vague on your actual research tasks. But at least it's a starting point. So ask for a copy of your proposal. One thing I'm going to talk about is building a mentoring network. This includes postdocs and senior PhD students in your group. They often can be sources of ideas of things that you can do for your PhD. So it's worth talking to them. When someone graduates with a PhD, they write a dissertation. The last chapter of the dissertation is conclusions and future work. Now, frankly, usually it's pretty boring. These are the incremental next steps we could do in the work. But sometimes the PhD student is outlining a new area of research, and he or she might expand upon that in the future section of his PhD. And this can be quite valuable. So that is worth looking at, particularly someone who's recently graduated from the same group, and see what future work they identify, particularly if they've taken a broader view rather than a shallow view. Analyze the state of the art, including literature review. I'll talk about that more in a moment. That can be a source of ideas, but it can also be a trap, and I'll get to that. Blue skies brainstorming can or cannot be valuable. As I said, it's driven by the research solution. I've had more than one project where we said, well, we've got this technology we can do something with. What should we do with it? And that actually can be a useful way to approach things. Driven by curiosity. Sometimes you play with a new idea just because it's a new idea and something interesting spans from it. I'll give an example of that. As identified by requests for proposals from funding sources. This can actually be quite valuable. National Science Foundation, but more particularly DARPA and Semiconductor Research Corporation, quite often put out fairly detailed requests for proposals. Now, your advisor may or may not write a proposal in response to that, but even if he doesn't, or he or she doesn't, then it is a source of ideas of what some people consider to be important problems. And they often have interesting starting points associated with them. I'll give you an example. A couple of years ago, there was a DARPA BAA on low temperature CMOS. The idea was to re-engineer the device and build interesting chips with it. Whether or not someone went after that as a research effort, it's an interesting idea to pursue. What can you do with these new low temperature devices? Eric Rotenberg and I have brainstormed about 12-issue processors and things like that. So sometimes, even if you're not part of a program, it can be useful to see what others are saying are important problems. SRC has put out their decadal research plan. It's 100 pages of problems being faced by industry, and this can be a useful source of ideas. As captured in research problem briefing documents, that's related to funding sources generally. But sometimes, quite often, agencies do studies on particular areas, and quite often they list research problems in that study. One of my most highly cited papers is one of those, a research study that I was involved in for DARPA. It's identified by SAGEs. Well, that's if you can find a SAGE. But quite often, individuals are willing to share things they think are worth pursuing. Now, once you have the problem, or at the same time, you've got to identify a solution as well. And of course, this can be daunting as well. What are the key innovations required to solve the problem? Quite often, this comes at the same time as working out what the problem is. And I'll give examples of that. Just to anticipate something we're going to talk about, combining ideas from different fields is a very fruitful way and quite an easy way to find new problems and new solutions. Given a big problem, deconstructing it into smaller problems and solving one of them can be very useful. I'll talk about the state of the art and focusing on shortcomings there in a moment. So let me talk about some general ways to innovate, to identify problems and solutions. And these are broad categories of innovation techniques. First one I'll cover, and I'm going to talk about them generally, then give some examples. But the first one I'll cover is design thinking. Steve Jobs was brilliant at this. Thinking about what do people need and what could be particularly valuable to people who need. I mean, at the time that the iPhone came out, the best thing on the market was we have tiny little keyboards that you should use your thumbs on, and next to a tiny little screen. And he realized that the touch screen was ready for exploitation and identified a set of innovations that led to the iPhone and the supporting ecosystem. And that's an example of design thinking. Can I put a computer in someone's hand that doesn't have this cramped keyboard and is easy to use as a computer, and that's been very successful. I'll give some other more closer to home examples in a few moments. Open innovation. What was meant here is not go out and reinvent Linux or something like that, but share your thoughts with others and get their feedback on our ideas. Many of you are working with industry. Quite often, industry is a very good source of ideas, and it can be quite helpful on the solutions side as well. And that can be very valuable. Industry-funded projects are often a very good way to end up structuring a PhD. And that's an example of open innovation, because you're open to interaction with people outside of your institution or outside of your group even, can be useful. Technology scouting. This is something that I've done a lot of. The idea is you seek external technologies and you combine them with other technologies to come up with very fresh ideas. Often combining ideas from different fields. This can be very valuable, to coming up with new ways of doing things. And finally, engineering deconstruction. This is, you've got an overarching goal, and can you break it down to a set of subproblems and tackle one of those subproblems as a PhD? And this can be once you identify the overarching goal, this can be a useful way to approach it. So let's look at some examples of these. I'm going to give some broad examples and then some of the examples from my specific research. The mouse, the computer mouse, believe it or not, was invented in 1964. You might say, believe it or not. I say believe it or not, because I didn't see my first mouse until 1985. But the one on the bottom, actually. The computer mouse was, can we point on a screen? The idea of screens and interacting them with things besides up and down arrows, left and right arrows, was starting to come out in the mid-60s. And someone had the idea putting a couple of wheels in a wooden box with a button and using it to create a pointer. And it worked. And it's led the first computer mouse. So that's an example of design thinking, solving a problem because it creates a new way of doing things. Then we spent 40 years improving the mouse. And one of these is on the screen here, where these track wheels on the one at the top got dirty. It wasn't very precise. And some people came up with the idea of having a pad with a set of lines over it, and an LED and a CMOS camera, a very small CMOS camera, that could track the changes in reflected light as the LED moved across the pad. And this was the sun mouse that you see there. This is deconstruction. This is improvement. and as much valid research as the original mouse. Here's another example from the 1960s. They'd already started building the Saturn V rocket. They weren't going to build a different rocket, but they had to get to the moon and the back with the throw weight of the Saturn V rocket. And this is a difficult problem because you only carry the order of 10,000 pounds to the moon. And the solutions are being bandied around all weighed more than that. So it was a difficult problem to solve. So the suggestion was, there's this famous memo in NASA of lunar orbit rendezvous. The idea being to land, you know what happened. They don't actually spell it out to you. And this is controversial because it required, in the moon orbit, to find two spaceships to find each other and dock. In lunar orbit, 250,000 miles away from Earth. And that was a scary prospect. Now, the theory for lunar orbit rendezvous had been worked out in the 1910s. But NASA actually adopted this because they is an example of design thinking and open-ended innovation, because they adopted a published solution and realized it was the best solution to their problem. But there's still problems to be solved, but then there were problems that had to be solved to make this happen. They needed to orbit and dock in lunar orbit. And the two keys to doing this was radar, which was already relatively mature at that point, and computers. And that's the Apollo guidance computer on the right there. You needed a computer to compute the burns to dock in orbit. Orbital mechanics is very difficult. Going faster often doesn't get you where you want to go. You just don't point your spacecraft and get there. You've got to calculate things precisely. So up until the Apollo guidance computer, a computer was a big set of vacuum tubes that sat in a room and failed every few hours. Now, you can't stuff one of those into a lunar module. So what they did is took evolving semiconductor technology with 2 gates per chip, 2 NOR gates per chip, and built a computer out of it. And this is the world's first embedded computer because it's embedded in a spacecraft. And it's the world's first computer that lasted for more than a few hours before crashing. In fact, it never crashed, at least on the missions. So these are a couple of examples, quite famous examples of innovation and how they approached it. Another example I've come across of open innovation is working with companies. This is more concrete and something you can do. For example, smart grid management. Some of you are probably working on. Companies have insights as to why their grids are working or not working. And they have data that they can probably share on how the grid works and what it looks like. And this can be useful in open innovation. And this is why it's useful to you to interact with industry, do internships, particularly with research organizations. You will get if you do a summer internship at a first tier tech company, you're going to learn so much because they're constantly going through the industry, trying to pick up what's going on, what the next big opportunities are, and sharing with employees so they can brainstorm on it. And often interns are involved in that process. So if you can get into a group that's doing that sort of thing, you will learn so much and get so many ideas that it's very useful and valuable. Any questions? Let me give a couple of personal examples. This is technology scouting. So I've done a lot of work in 3D-IC, and Intel put out an RFP to asking universities to do something interesting for them. And I went to Eric Rotenberg and said, well, I want to exploit this new technology, hybrid bonding. What hybrid bonding allows you to do is bond 2 chips together with about a micron pitch on the interconnect. And normally it's like 50 micron pitch. So about a micron pitch in the interconnect. Well, you see at the top right there, 2 chips bonded together. This is what we actually built. 2 chips bonded together, and these bonds are at an 8 micron pitch. We could have done them tighter, but we didn't need them tighter. So I went to Eric Rotenberg about this, and he knew that Intel was very interested in thread migration. And that was a research topic at the time, how to move threads between processes. And he and I brainstormed a bit, and we realized we could use these hybrid bondings to do very fast thread migration, transfer hundreds of registers, contents, between two microprocessors in one clock cycle. And we proposed this to Intel, got $1.2 million, built it with Rhett Davis's help as well, and it worked. And several students got their PhDs along the way because with the sub-problems that need to be solved, the architectural details, how to lay out the chips, how to do the physical design. I show the floor plans on the right. All right. So this is a combination of technology scouting, me and Eric, combining ideas from different fields, of open innovation. I went outside my research group to find ideas to go to Intel with, and engineering deconstruction, breaking the problem into sub-problems and handing those sub-problems off to individual PhD students. And this worked very well. Here's another example that was actually a little more curiosity-driven. I asked one of my PhD students if he could look at circuits that didn't go off a DC supply voltage, but worked off an AC supply voltage. And Peter was the student, and he came back to me with a circuit that could be powered off an AC supply voltage, really an RF supply voltage, a few hundred millivolts of RF signals. And this is an interesting thing to look at, and we played with a little. But the question was, what's the application? So this is the solution, looking for an application. And I realized a good application would be RFID. It's not as sensitive as other RFID chips, but it's a lot smaller. At the bottom here, I've shown a picture of our chip compared with the industry state-of-the-art. So it's a lot smaller, that's a lot cheaper, and tends to use for particular applications, which we're exploring right now. And there were problems we had to solve along the way, and this led to a stream of 3 PhD students who solved these problems. More recently, I've been doing a lot of work at the intersection of machine learning and VLSI. And this works very well because we take emerging machine learning techniques and apply them to problems in VLSI that haven't been solved. With Priyank Kashyap, we worked out how to macro model circuits using machine learning. With Schaefer Naman, we're looking at floor planning using machine learning. And this combining state-of-the-art machine learning with problems in VLSI. And this is actually in a company-driven center. I run a center here on campus with other universities, which the companies propose problems and we propose solutions. And the problem formulation aspect is very straightforward in this. So that's identifying the problem and identifying the solutions. Are there any questions or comments, please?
Professor Franzen?
Yes.
Yeah,
yes.
I just had a question. Is there an online list of, you mentioned RFPs, is there like an online list of agencies, DARPA or the Air Force or something that, you can find out, okay, here's a long list of RFPs that here are the projects that we're interested in? Is there something like that?
Question is online, is there a list of agencies who have problems like this? And I'm not aware of such a list. You have to go to the individual agencies' websites. DARPA is a call for solicitations. SRC is a decadal plan on their website. So next I'll talk about any other questions, please. Yes. A good question. The question is there a timeline to identify the research problem and identify the solution path? The quicker, the better, before your advisor loses patience. Hopefully he'll give you about a year to do that. That's probably a good time frame. Any other questions? Okay, next to talk about the analyzing the state of the art and the literature review. Of course, there are many sources of analyzing the state of the art. There's not just the published literature, in IEEE Explorer and ACM. There's also websites. Wikipedia is actually pretty useful, and corporate publications. Other sources of interesting they're useful to are review papers. Quite often, people write review papers on particular areas, and that can be very useful to get you up to speed in a particular area. Quite often, PhD students, their first publication is a review paper of their particular topic. So that can be useful as well. And invited and keynote talks at conferences tend to give big picture views of things that are going on and what the emerging problems are. I'm going to talk specifically about literature review. You're expected to do a literature review and to maintain one for your PhD. This is chapter 2 of your dissertation. And so you have to do this. You've probably worked out how to do this by this point. I'm not going to belabor this. But you're going to do a set of searches. You're going to keep your search terms so that you can refine those searches. And you're going to analyze what you hit upon and selectively read a few of them. I'll get to that in a moment. From this, you establish a big picture view of what the field looks like, where the recent advances are, and to some extent what the outstanding problems are. And this gets you a bibliography which you maintain until you write your PhD. So in principle, you can use the gaps identified in the literature review as a starting point for your PhD. This is a valid use of a literature review. It's also, though, a little dangerous. And there are two big dangers. One is you might read a paper and you might realize they could have done this better. Or they had left this piece of work undone. I can go in and fill in that piece of work. Well, the chances are they've realized that as well. And unless the student has graduated or the project ended, they're doing that work. And so you're essentially competing with a group that's already ahead of you. So that can be quite dangerous. The other thing to be quite careful about is that this sort of thinking can lead to incremental work. We published a paper a few years ago using convolutional neural networks to do design rule checking of chips, a lot faster than a regular design rule check. And a year or so later, someone contacted me asking for the data. And we're willing to share the data, that's not a problem. But my reaction was internally, I didn't say this to the person who contacted me. My reaction was internally, you're going to do a PhD improving our method by 10%. And I think, okay, that's fine. You can probably get a PhD out of that, but it's not very exciting. All right, just working out, I could read, so it's very dangerous to read a paper and say, oh, I can do better than that, particularly if it's an incremental improvement. Nonetheless, sometimes you can recognize hidden gaps in the research, use that to guide your PhD. The other issue in literature search is you're going to get hundreds of hits, and you've got to sort through these fairly quickly. And that's what I'll talk about next, is how to quickly focus on what influences or informs your research. And this leads to a short section here I have on how to read papers. You don't read a paper by starting the abstract and carefully reading it to the conclusions. I haven't read a paper like that in years. And I argue that you should never. And you should take it in stages. Yes, you should start with the abstract. You'll see the abstract in IEEE Explorer, so that's actually very handy. Now quickly able to sort out whether the paper is relevant to you or not. If it's potentially relevant, the next thing I look at is the introduction, because that will define the problem that's being addressed. It'll also say what the contributions of the paper is. Every paper should have a sentence that basically says the key contributions in this paper are. This includes your papers. They should have that section in them. The key contributions of this paper are. And that tells you what the key contributions are, and you can decide whether that's useful or not. Another thing that's actually useful to do in the introduction, particularly with a paper that's going to be more valuable to you, is for you to think about how you would solve the problem before you read how the author solves the problem. This will engage you with the paper a lot better than passive reading. Then what I do is skip to the conclusions and read what they conclude. Because this tells me whether they actually worked out anything worth a damn or not. All right? if the conclusions say, wow, that's interesting, they work out something really valuable here, or if the conclusions basically say, we made progress on this problem, but without really solving it, then the second one, the paper's less valuable to me. Then what I do is look at the figures. A well-written paper should be readable from its figures, and then read the text. So it's only at the end there that you read the paper in full, knowing it's relevant to your work. So this leads me into the PhD qualifying exam. That changes by group. So I can't talk about a departmental-wide standard, but some groups require a literature review. So we just covered that. Some groups require a publication, a conference-like paper, and it should be a lot easier to pass your exam if that paper is published. And some groups, particularly the computing group, has a written exam. But the first format in particular is covered by doing the steps that we talked about a couple of pages ago. By the way, you're meant to complete your qual by your end of your second year here. Not that anything happens if you don't. So next thing I'm going to talk about are proposals. And I'm talking about this for a reason. The next exam after your qual is your prelim. And it is meant to be a research proposal. And it usually isn't. In fact, I looked through the prelims of the last few years in my group to see if I could find a good one. Couldn't. Nothing critical, because what most people do for the prelim is do most of their work, write it up, and they have a bullet list of things they want to do complete. So it's not really a proposal at that point. It's really a polish-up plan. But really, it should be a proposal. And furthermore, anyone with a PhD should be able to write proposals. Even if you go to industry, you'll be pitching new ideas, and you should learn how to pitch new ideas. So I'm going to spend a couple of pages talking about how to write a proposal, not the mechanics of it, but what should be in it for it to be successful. And the model I'm using for this is the High-Meyer Catechism, which is what DARPA uses to evaluate proposals. It's named after a DARPA program manager from the 70s, but it's a list of questions that any good proposal should, to some degree or another, answer. And what I'm going to talk about these and then give an example from one of my proposals. The most important thing is, what are you trying to do? And explain it in plain English. A lot of people go straight to the mathematics or assume that the reader knows as much as they do, maybe minus a few months. That is very common in PhD students, even common in beginning professors, to assume that the reader is very knowledgeable. They're not. It should be targetable to anyone in your general field, not just to deep experts. And a lot of people write proposals that are only understandable by deep experts, and that's dangerous. You should be able to articulate the objectives, at least, with no jargon. Now, the details can come later, and they can be technical. But when you're outlining what the proposal is about, it should be easy to read and understand. You should be improving something. You shouldn't just be doing something because it's an interesting idea. You should be improving something that exists. How's it done today? And where is it failing? Why does it need improvement? What is new about your approach? Where is the novelty in what you're proposing? And you're not just rehashing existing ideas. Because a lot of people write proposals that are rehashing existing ideas. Who cares? What difference does it make? We're engineers, right? So we generally want our ideas to have an impact. We want to be able to change some way of doing something. Most proposals have some sort of risk management plan in them, or at least address the risks in the proposal or the effort. And of course, you'll need the mechanics of how much it will cost and how long it will take. This is not relevant to a PhD student. It will take the rest of your PhD and it will cost you stipend. So there's nothing much to expand upon there. But generally in proposal, you do discuss these things. And finally, how do you measure it was successful? And how do you measure it along the way? You can't really ask someone to wait 3 years and then they'll find out if it worked or not. There should be some intermediate milestones that are achievable and some metrics to measure things. So here I'm going to give an example of one of my own proposals. You probably can't read the details, and that's okay. The idea is, well, I wrote it there in the first sentence. The objectives. NCSU will conduct a study on the feasibility of doing trusted chip fabrication using an untrusted CMOS source and a trusted 3D integration fab. There in one sentence, I got what the proposal was about. And by the way, this was sort of study. We then went on and built it. So this led to $2.5 million of funding. And it worked. This is the idea is to split manufacturing between untrusted sources and trusted 3D integration sources. How is it done today? I had a section on that. This talks about obfuscation, which is our objective here. Our objective here was to obfuscate the design intent, and talks about the state of the art in split fabrication. There was another agency doing work in this area at the time. It was very hard to use. What's new? In anything I write, I try to have one central figure that captures most, if not all, of the proposal. This doesn't capture all of it. There's the CAD side, which is a separate figure, which I didn't put here. But this captures the physical technology. And I explain what is new here. Measuring success. We're engineers. We love to measure things. Any research project should have metrics. Things you can measure that show whether it's successful or not. And in your research, you should be measuring your ideas against those metrics and comparing what you achieve in those metrics with what others achieve. So here we have some metrics, and we had to schedule the milestones for the conduct of the proposal. And this section combines who cares and risk management. Who cares, I say, a long-standing issue in the defense community is how to build a trusted integrated circuits in an untrustworthy supply chain. That's who cares. And then I explain where we're using known techniques. We're not inventing new technologies. We're just inventing new design methods. And I explain that as managing the risks. So like I said, this meets the elements, the High Catechism. It was to DARPA, who respects that list, but that list applies to any proposal. And this and the follow-on proposal to actually build it was successful. Finally, I'll get towards the end of your PhD when you write your dissertation, do your final defense. There's a very standard outline for dissertations. You have the introduction, which motivates the problem, and very importantly, has a section on what you've done that is new. What are your novel contributions? You have a background chapter, including literature review. You then have your technical chapters, conclusions and future work. And I ask my students to have appendices of all the details. If there's code, the code is in the appendices. So if we lose everything, we can rescan the code. The design layout is in the appendices. PhD is typically about 150 to 250 pages. These are double spaced. I suggest using LaTeX rather than Word because it's much easier to keep track of references, much easier to do mathematics. And it is really best, and I'll come back to this, to construct core chapters from accepted publications. Write the papers first, then write the core papers, not the other way around. Why not the other way around? Because in a thesis, you tend to be a lot wordier than you do in a conference paper. In technical paper, you're usually given a page limit, trying to fit in that page limit, so you write concisely. It's very hard to write it's very much easier to write the concise version first, not the wordy version. Now, this is the part I promised that I consider to be key to a successful PhD, and will not surprise you at this point. And that is that a PhD student should be primarily focused on producing a sequence of papers. Publish, publish, publish. That should be your mantra. That should be your goal. Why publish, publish, publish? and particularly do so in first tier or second tier venues. Right? Why? You come to your PhD exams. I can give you concrete examples, but I'm not going to name students. Student A, several published papers, goes to the exam, basically presents those papers. Committee thought, not sure about this, not sure about that. But he's published this. It's been gone through the rigors of peer review. It's been accepted. I'm not going to question it. And the student sails through the exam. Student B, published in one crappy workshop, gets to his final exam. Oh boy, did he have a tough time. And that's because he didn't have that rigor of peer review to establish the novelty of his work. Secondly, it's a starting point for writing your dissertation. Write the papers first, turn them into chapters, and you've written most of your dissertation. You can write your dissertation in 3 months that way, not taking most of a year. And finally, it keeps your advisor happy. Your advisor is measured on publications and citations and impact that can be measured in other ways. And so publications are very important to your advisor. Any questions on the key to success? Now, this is easy to say, but harder to do. But if you focus on it, what's going to be my next publication? Discuss it with your advisor and constantly think about it. You can drive your way through the PhD process. I thought I'd put in one slide on generative AI. We're going to write a departmental policy soon. It'll basically be this. But some of you are probably using it. And just a word of caution here. It can be very useful. I'm not denying that. But just a couple of things to think about. Some venues don't allow it. Surprisingly, it's more the venues in machine learning that don't allow it. The IEEE allows it if you acknowledge it. But if you use AI to help generate the prose in your paper, there are rules about that in the publication source. And you've got to follow those rigorously. It's pretty easy to detect when AI is writing something. Why is that? Because we don't write as good as it does. ChatGPT writes a lot better than I do, and probably writes a lot better than any of you do. So you get something that's well written, you pretty much know that these days is probably written with ChatGPT. So you've got to be careful about your intended publication venues. You lose copyright. You can no longer copyright your dissertation. You might, at least for the sections that use AI. And for code, any code that's generated with AI, you don't own the copyright. It incorporates the IP of others. And that can be a bit of a danger when you're claiming something for yourself. It potentially exposes your IP to others. Now, there's ways of avoiding this, but if you just use the tools as they are, you're basically giving away your IP to the tool. You say, oh, I got this code, can you help me debug it? You're sharing that code with the world, and you've lost your intellectual property protection. And of course, as you're aware, it often hallucinates, it's often inaccurate. There was an example written up recently of a lawyer who was being lazy and used ChatGPT to write his brief. He went to court with his brief, and it was discovered that not a single citation in that brief was an actual case. It completely fabricated the entire brief. And that lawyer got into a lot of trouble. But it can still be useful. It can probably be quite useful in your literature review sections and write the background parts of your work. As I said, we're going to develop a formal policy. Are there any questions? So finally, I've got only a couple of slides left. Your advisor relationship. PhD comics, by the way, you should look for this. Particularly as you evolve later in the PhD process, you'll be able to relate to many of the comics very directly. They're quite funny to people who've done PhDs or doing PhDs. So this one is what students wish their advisor was like and what advisors wish their students were like. And it's very true. So I'm going to talk about both of these. Qualities of good PhD students. These are the things you want to hear about yourself from your advisor. And I separated out the top three as the most important. As I said, constantly seeking to publish in first-tier venues and with impactful papers. Advisors love it when their students are talking about publishing. Sources of new ideas. A student who sees a set of projects is particularly great. When someone starts a new field of research within a group, and at least 3 or 4 other dissertations. Productive delivers on time is not. I don't have to say that. That's pretty obvious. Some lesser issues, lesser qualities, does not require a lot of day-to-day help. Faculty are pretty busy. If someone's demanding hours and hours of their time, they may grow to resent it. Quite often, faculty involve PhD students in keeping their funding sources happy, doing briefings to their funding sources, things like that. And that can be quite good. Student who keeps on track towards degree completion is relevant. The median time to finish a PhD in this department is 6 years. And it shouldn't be that. It should be 4 or 5. And quite often it's because students bounce around between topic, bounce around between group, and sometimes it's quite often because students get comfortable and become long-term PhD students. There's even a good PhD comic on that. Communicates well. Successful students have multiple sources of mentorship. They don't just rely on their advisor. And mentors others. Senior PhD students should be mentoring junior PhD students. Now, to be fair, all the colleagues are good advisors. And feel free to add to this list. Helps the student get started. A good advisor should at least have a starting point for a new student, even if all the details aren't worked out. Helps the student overcome difficulties and gives feedback. And so tied to that is meets regularly and is reasonably available. Allows students to have ownership of their ideas. Comments when they contribute to projects. Make sure, constantly tells others that it's the students doing the work, not the advisors work on his own. Really openly acknowledges the students' contributions to the projects. Some advisors are bad at this. They want to make it seem like everything is theirs. Most are good at it, so don't be too worried. Well, the second last one's a little tough. Allows the student to finish in a timely fashion. Now, when should a PhD end? It's a bit like asking how long is a piece of rope. When I was a student, we used to joke about the weight test. You've got to graduate when your dissertation weighed enough. Hence the 150 to 250 pages. But there should be, a project should be taken to some natural point of completion. It should be substantive enough, and the loose ends should be reasonably tied up. Now, some advisors tend to keep their good students back to do more. Others, but most are quite happy to let their students move on once a reasonable body of work is finished. Again, what's reasonable is very much open to debate. It's very hard to measure this. And finally, and quite importantly, maintains a positive and supportive culture. I hope your advisors have most of these qualities, and I hope that works out for you. So that brings you to the end. You're in this game of doing a PhD to work out new knowledge, and that's what you're measured on. How good is your new knowledge? Your new knowledge can be theoretical, can be applied. There are many ways to get started and work out research problems and solutions to work on. It takes getting out of your shell a little bit, talking to others, scouting out there for ideas, scanning out there for technologies and other areas that are relevant. And that last one is particularly useful to combine ideas from different areas. You have to understand the state of the art and do a literature review, but most of you will work out how to do that. You have to learn to write a good proposal, at least hopefully. And AI can be quite useful, particularly in background materials. And finally, and most importantly, publish frequently. Use that as the basis for the rest of your PhD, your rest of your PhD deliverables. That's all I was planning to present. Are there any questions, please, or comments? Yes. How to include data sets and publications? Put them on a GitHub and refer to the GitHub or the archive in the paper. Do discuss it with your advisor. Many people like the idea of openly sharing your data and publishing the data set. Some people don't. And sometimes you can't because the data set is proprietary or something like that. So just make sure you have permission to share it. Yes. The question is, how do you avoid incremental ideas and do innovative ideas? And that's a hard question to answer. As I said, it's easy to fall in the trap of focusing on incremental ideas. And a lot of people do that, and that's okay. It's not very exciting from a PhD perspective, and it's probably hard to get funded. And working out the truly innovative ideas. My favorite method is combining ideas in different fields. Even the computer mouse. At the time, people were starting to think about using screens rather than just text line interfaces on computers. And there wasn't a big step from realizing you want to interact with the whole screen to realizing you needed to be able to point on the screen. And that led to the idea of the mouse. So it was an evolution of trends at the time. It wasn't just, oh, I'm using punch cards. I'm going to use a computer mouse instead. Because punch cards are still very, very common back in that era. My first computer program was written with punch cards. There's often a body of knowledge developing. But combining ideas in different fields, that's very valuable. Any other questions? There's chats online? Okay. You're welcome. What are good suggestions to build self-confidence? Present. It doesn't have to be an external publication if you're presenting within your group. Being able to present your ideas publicly or semi-publicly, getting questions about them, answering those questions. I spend a lot of time talking to industry. And the reason is I get good feedback from them. They say, what have you thought of this? Oh, that's a good idea. What about this aspect of your work? Is there a problem? Oh, that's a good point. We should look at that. It's very, very useful to talk to others. And at the same time, it develops your self-confidence, even if it's internally here. Industry versus academic career. Who wants to be an academic in this room? Okay. It's very hard to be an academic, to become an academic these days. When I graduated, the people didn't do postdocs. They went straight to university positions. That's no longer true. Most people do postdocs. So you have to anticipate doing that. And there's one key aspect of being recruited as an academic. And I'll give you one guess as to what it is. Lots of first-tier publications. I had seven publications when I finished as a PhD student. And that was the key to getting me an academic position. So lots of first-tier publications is key to becoming an academic. After you're an academic, you tend to get more free rein than an industry person. So you can go after a diverse set of problems and a diverse set of solutions. And that tends to be the difference between industry career and academic career. I could expand on that, but I'll probably do for now. And the sound is better. Okay. Are there any other questions, please? I can work out this mouse. Yes. Question is, how do you differentiate first tier and second tier publications? So in journals, the first tier for us is usually the IEEE journal. There is Nature as well, but that's kind of rare for engineers to publish in Nature. There's Nature that they're oriented towards engineers. But for us, it's the IEEE publications, as opposed to Elsevier or some of those other publication spheres for journals. For conferences have reputations. And this goes a lot by their acceptance rate. For example, ICCAD, DAC, ISSCC in our area. These are low acceptance rate conferences. Now the second tier of conferences are usually still quite good. But then there's a bottom tier which kind of accepts everything. And that's less, it can still be useful. You can get a publication that way, particularly if you've got low value work that you just want to get out there. But is less useful in building your reputation. Any other questions? Yes, I'll email the recording. What was it? What is it like to build a lab? So I think you mean as an academic. So what's it like to build a lab as an academic? You get to write lots of proposals. And I'm serious there. In general, I focused on writing proposals rather than other tasks, because it's money that feeds the pipeline. And if you don't have the money up front to feed the pipeline, you can't finish the pipeline. Now, there's other views on that. Some people focus more on having high impact, and that's okay. But as an academic, if you don't raise money to pay students, to buy equipment, to do experiments, then life is harder, particularly in more experimental fields like I work in. So that's what you have to do to build a lab. It probably took me, it took several years before I was able to buy equipment from proposals. But we started building things from day one. Any other questions, please? Well, great. Thanks very much for coming, including those online. I hope this is somewhat useful to you. I appreciate you coming. There's an online question I missed. How do you manage failure? Sometimes we come up with new. Okay, how do you manage failure? There's an online question on this. Well, one way to look at this is you never fail. Even in the less successful projects, you learn things that are still useful and valuable to you. So we have a joke in academia. We call it declare success and move on. You say the project was successful. We learned the following things, and now we're moving on to the next topic. So that is a generous way to handle failure. There's always something you can learn from failure. And if you're not failing, you're not taking enough risks. So failure should be normal. Now, for individual PhD students, it's a little more difficult, because if it fails, you've got to move on to another topic. But for an academic advisor, if he or she isn't failing occasionally, they're not taking on enough risk. Let's see if there's any other questions here. How long does it take to build a lab? Usually about 5 years. Okay, that's it. Thanks very much. Let me stop the...
Recording is complete.
Welcome. the recording. Yeah. I didn't. Are you sure you want to?